So, you've probably heard the term protocol thrown around, especially if you've ever tinkered with your Wi-Fi settings. But what does it actually mean? Think of it like a language. When you talk to someone, you both agree to use the same language, like English. You follow certain rules, grammar, sentence structure, so the other person understands you. If one person speaks Spanish and the other speaks Japanese and neither knows the other's language, you're just making noise. There's no real communication happening, it's just a lot of confusion and nothing gets done. Network protocols are exactly that. But for computers, they are the agreed-upon rules and languages that all our devices use to talk to each other. Your iPhone, your Android phone, your Windows laptop, your smart TV. They all come from different companies and run different software. But they can all connect to the same internet and understand each other. That magic isn't an accident. It's because they all follow a very specific set of rules or protocols to send and receive information. Without these shared rules, the internet as we know it would be pure chaos. It would be a digital Tower of Babel. These protocols aren't just one single thing. They're a whole collection of rules working together. It's like a team. One protocol might be in charge of making sure your message gets to the right place. Another protocol's job is to check if the message arrived in one piece, without any errors. Yet another one is responsible for formatting the data so your web browser can actually display it as a web page instead of a jumble of code. You use these protocols every single second you're online, even if you don't realize it. When you load a YouTube video, you're using protocols. When you send an email, you're using protocols. When you ask your smart speaker for the weather, you're using protocols. They are the silent, invisible foundation that makes our entire digital world possible. So, for the next few minutes, we're going to pull back the curtain and take a look at what's really going on when you click that link or hit that send button. It's pretty cool stuff. Okay, so how does your data actually get from your computer to, say, a server on the other side of the world? It doesn't just travel in one big chunk. That would be super inefficient and clog up the internet's highways. Instead, your data gets broken down into tiny, manageable pieces called packets. Think of it like sending a massive encyclopedia through the mail. You wouldn't try to stuff the whole thing into one giant, building-sized envelope. You'd send it one page at a time, in hundreds of small, standard-sized envelopes. That's exactly what happens with your data. Each one of these packets is like a tiny digital package. It contains a small piece of the data you're sending, part of an email, a sliver of a photo, a few frames of a video. But it also has a label on it, kind of like an address label on a real package. This label has some really important information. It includes the IP address of where it's going, the destination, the IP address of where it came from, the source. It also has a sequence number, which is super important. It tells the receiving computer the correct order to put the packets back together. Once these packets are created and labeled, they're sent out onto the internet. And here's the crazy part. They don't all have to take the same path. Just like your GPS might give you different routes to avoid traffic. The internet sends these packets along the most efficient paths available at that moment. One packet might travel through routers in New York and London, while the next packet from the same file might go through Atlanta and Paris. When the packets finally start arriving at their destination, the receiving computer gets to work. It uses the sequence numbers on each packet to reassemble them in the correct order. It's like putting together a puzzle. It checks to make sure all the packets have arrived. If one is missing or got corrupted along the way, it sends a message back to the original computer asking it to resend just that one missing piece. Once all the pieces are there and in the right order, the file is recreated and you can see the web page, read the email, or watch the video. So, we've talked about packets. But what's the system that manages all of this? That's where TCP/IP comes in. You've definitely seen this acronym before. It stands for Transmission Control Protocol and Internet Protocol. It's not just one thing, it's a suite or a pair of protocols that work together as the fundamental building block of the internet. Think of them as the co-managers of the internet's entire postal service. They have different jobs, but they work as a perfect team to make sure everything runs smoothly. First up is IP, the Internet Protocol. Its job is pretty straightforward but incredibly important: addressing. It assigns every device connected to the internet a unique IP address, which is like a street address for your computer or phone. When a packet is sent, IP makes sure it has the correct to IP address and the correct from IP address. Its main goal is to get the packet from the source to the destination, routing it from one network to another across the globe. IP is all about the delivery address, but IP by itself is a bit of a best effort delivery system. It doesn't guarantee that the packets will arrive. It doesn't guarantee that they'll arrive in order. That's where TCP, the Transmission Control Protocol, steps in. TCP is the reliable one. Its job starts before the packets are even sent. It establishes a stable connection between the two computers, like a digital handshake, to make sure they're both ready to communicate. Then it's TCP that takes the big file and breaks it down into those numbered packets we talked about. It keeps track of every single one. After IP does its job of routing the packets, TCP on the receiving end takes over again. It collects all the incoming packets. It checks the sequence numbers. It puts them back in the right order. This is the crucial part. TCP is responsible for error checking. It verifies that all packets arrived safely. If a packet is missing or damaged, TCP sends a request back to the sender to retransmit just that specific packet. It ensures a reliable, complete, and ordered stream of data. So IP handles the addressing, and TCP handles the reliability and order. Together, they are the powerhouse duo that makes the internet work. Alright, so TCP IP gets the data there reliably. But how does your browser know what to do with that data? How does it know to display it as a web page with text, images, and links? That's the job of HTTP, the Hypertext Transfer Protocol. This is the protocol of the World Wide Web. When you type a web address and hit enter, you initiate an HTTP request. Browser sends, "Hey server, send me the web page." HTTP is a request-response protocol. Your browser, the client, sends a request. The web server sends a response. Response contains the HTML file, includes CSS for styling, and JavaScript for interactivity. The server also sends status codes. Example, the infamous 404 not found. That code means the server couldn't find the file. Most web addresses today start with HTTPS, not just HTTP. The S stands for secure. HTTPS equals HTTP plus security layer. It uses SSL TLS, secure sockets layer, and transport layer security. That layer encrypts communication between your browser and the server. Encryption means data is scrambled into unreadable code. Why it matters. HTTP sends data in plain text. On public Wi-Fi, someone snooping could read everything. Passwords, credit card numbers, private messages, it's all exposed. With HTTPS, intercepted data looks like a jumble of characters. The padlock icon in the address bar tells you you're on HTTPS and encrypted. It's an absolute must-have for modern web browsing. So we know that every server on the internet has an IP address, which is a string of numbers like 172.217.14.228. But let's be real, nobody can remember that. You don't type a bunch of numbers into your browser to get to YouTube. You type youtube.com. So how does your browser know that youtube.com means it should connect to the server at that specific numerical IP address? This is where the Domain Name System, or DNS, comes in. DNS is, for all intents and purposes, the phone book of the internet. It translates the human-readable domain names that we type, like google.com and mkbhd.com, into the machine-readable IP addresses that computers need to actually locate each other. When you type a domain name into your browser, the very first thing that happens before any HTTP request is sent is a DNS lookup. Your computer sends a query to a DNS server asking, "What is the IP address for youtube.com?" It's kinda like looking up a friend's name in your contacts to find their phone number. This process happens almost instantaneously, but it's definitely a multi-step dance. First, your computer checks its own local cache. If it has the IP address saved, it just uses that. If not, it asks your router. If the router doesn't know, it forwards the request to your internet service provider's DNS server. If that server doesn't have the answer, it goes up the chain to one of the world's root DNS servers, which then directs the query down the correct path until the IP address is found. It's a global, hierarchical system designed to be incredibly fast and resilient. Without DNS, the internet would be practically unusable for humans. Imagine having to memorize dozens or even hundreds of numerical IP addresses for all your favorite websites. DNS provides that critical translation layer that makes the internet friendly and accessible. It works silently in the background, making complex network navigation feel as simple as typing a name. It's a simple idea, but honestly, it's one of the cornerstones of the entire internet. Now let's switch gears from browsing websites to sending an email. This process actually uses its own set of specialized protocols, and the main player for sending mail is SMTP, which stands for Simple Mail Transfer Protocol. When you hit send on an email in Gmail, Outlook, or Apple Mail, your email client doesn't send the email directly to your friend's computer. That would be wildly impractical since your friend's computer might be turned off. Instead, your email client talks to an outgoing mail server using SMTP. Think of SMTP as the post office clerk, or maybe the blue mailbox on the corner. Its job is to take your letter, your email, and start it on its journey through the postal system. When you click send, your email client connects to your mail provider's SMTP server, like smtp.gmail.com. It uses the SMTP protocol to say, "Hello, I have an email from this address and it needs to go to this other address." It then hands the email, the headers, the body, any attachments, over to the server. The SMTP server then takes responsibility for the next step of the delivery. Your SMTP server then looks at the recipient's email address, specifically the part after the @ symbol. It uses DNS, see, it all connects, to find the mail server responsible for that domain. It then connects to that destination mail server, also using the SMTP protocol, and transfers the email. The email now sits in a mailbox on the recipient's mail server, just waiting for them to check their mail. SMTP's job is purely about the transfer of mail from server to server across the internet. So, SMTP handles the sending, but what about receiving? When your friend opens their email client to check for new mail, they're not using SMTP. They're actually using one of two other common protocols. POP3, which stands for Post Office Protocol 3, or IMAP, which is Internet Message Access Protocol. POP3 typically downloads the email from the server to your device and then deletes it from the server. IMAP, which is much more common today, syncs with the server, so your email is accessible from multiple devices, your phone, your laptop, your tablet, and it all stays in sync. SMTP sends, while POP3 or IMAP retrieve. Sometimes you need to do more than just browse a website or send an email. You need to upload large files or download large files. Web developers uploading site files, scientists sharing massive data sets. For these heavy-duty transfers, we use FTP, the File Transfer Protocol. It's one job: move files between computers. FTP works differently from HTTP. It uses two separate connections between client and server. Control connection used to send commands, logging in with username and password, navigating folders, issuing download or upload commands. This connection stays open for the whole session. Data connection opened only when a file is transferred. A new connection for each file. File sent, then closed. This separation lets the control channel stay active while temporary data connections handle the heavy lifting. FTP is not secure by default. It sends username, password, and file data in plain text, a significant security risk. FTPS, FTP over SSL, TLS, and SFTP, SSH File Transfer Protocol. Both wrap communication in encryption, making them the preferred choice for sensitive file transfers today. So now we know about all these different protocols. Let's, see how they all work together in a real-world scenario. Imagine you wake up, grab your phone, and decide to check your email and then look at a news website. The moment you open your email app, your phone is already hard at work. It uses IMAP to connect to your email provider's server, syncing your inbox and downloading the headers of any new messages that have arrived overnight. You see an email from a friend with a link to a news article. You tap on the link. The first thing your phone's browser does is talk to a DNS server. It sends a request asking for the IP address associated with the news website's domain name. The DNS server quickly responds with the numerical IP address. Now your browser knows where to go. It then opens a connection to that IP address. Since most modern sites are secure, it will use HTTPS. This initiates a handshake process to create a secure, encrypted channel between your phone and the news website's server. With the secure connection established, your browser sends an HTTPS request to the server, asking for the article's webpage. The server finds the file and sends it back, but it doesn't send it in one big piece. TCP on the server's end breaks the web page's HTML, images, and other components into thousands of tiny numbered packets. The IP protocol then puts an address on each packet and sends them out across the internet. They travel through countless routers, taking different paths until they reach your phone. As the packets arrive, TCP on your phone gets to work reassembling them in the correct order, checking for errors and requesting retransmissions of any missing pieces. Once all the pieces are assembled, the HTTPS protocol takes over, decrypting the data. Finally, your browser's rendering engine interprets the HTML, CSS, and JavaScript to display the formatted news article on your screen. All of this, DNS, HTTPS, TCP, IP, happens in the span of a second or two. It's an incredibly complex symphony of protocols, all working in perfect harmony just so you can read the morning news. So, after all that, it's pretty clear that network protocols are the invisible engine that powers our entire connected world. They're not something most people ever need to think about, and that's by design. They are the ultimate "it just works" technology. Silent, agreed-upon rules of the road that stop the internet from becoming a chaotic mess. Without standardized languages, your Apple device wouldn't be able to talk to a Google server, and your Windows PC wouldn't be able to load a website hosted on Linux. Every simple action you take online is the result of a complex chain of events managed by these protocols. Sending a simple LOL in a chat message involves a cascade of DNS lookups, TCP handshakes, and data packet transfers. This standardization is what allows for innovation. Because the foundation is so solid and reliable, developers can build amazing new apps, services, and platforms on top of it without having to reinvent the wheel every single time. They can trust that the underlying network will handle the communication reliably. Think about the sheer scale of it all. Billions of devices made by thousands of different manufacturers, running countless different versions of software, all communicating with each other flawlessly every single second of every single day. This is arguably one of the greatest collaborative engineering achievements in human history. And it's all made possible by a shared commitment to a set of open, well-defined protocols that everyone agrees to follow. So the next time you load a web page, send an email, or watch a video, just take a moment to appreciate the silent, tireless work happening in the background. From TCP/IP managing the traffic, to DNS acting as the universal translator, to HTTPS keeping your data safe. These protocols are the true unsung heroes of the digital age. They are the fundamental grammar of our global conversation, the bedrock upon which our entire modern society is built. And understanding them, even just a little, gives you a whole new appreciation for the magic of the internet.